All right, I have a quick question, but it's really important nonetheless. Can change occur in an instant? Because if you think about it, change is described as making something different, and that normally occurs over a period of time. But if change happens over time, can it occur in an instant? A very small moment, a jiffy, a moment, an instant. There's two ways to look at this problem. You can say no, it can't, because an instant is zero time. It's, instantaneous. But if you also think about it, it has to occur at an instant, because change wouldn't be possible if each and every instantaneous moment over that interval was unable to change. No change would be able to happen. So if you think about it, change has to occur in an instant. But that's really weird to think about. So let's stick around and you can find out proving that change can occur in an instant. And you can also learn a little bit about today's topic, limits. Welcome to Learning Calculus, and for a quick introduction and why I'm qualified to teach you some calculus, I think that math is super fascinating. I just recently graduated and earned a 5 on the BC Calculus exam, which is equivalent to Calculus 1 and Calculus 2. And when I grow up, I hope to teach some sort of calculus or math as a teacher. And remember, the best way to improve at calculus is by doing calculus work. So let's take a look at this function. We have f of x is equal to x squared minus 4 divided by x minus 2. And it just forms a line when you plug it into Desmos. But you can see something interesting. As you approach 2, you see that the line goes through 4. But if you plug in x equals 2, you get undefined because you end up getting 0 divided by 0. X squared is 4, minus 4 is 0, and then when you plug in 2, 2 minus 2 is 0. But what mathematicians have found is that even though at 2 itself, it is undefined, you can say that the limit of f of x as x approaches 2 is still 4. And you can see that just by looking at the graph. The line still goes through 4. In fact, if you look at it on Desmos, it looks like x equals 2 doesn't even have an issue. But it does. So you can say that the limit means that on some interval that contains a value g, except possibly g itself, the limit of f of x as x approaches g is still some value L. That's what a limit is. It basically means that as you approach something, how does something approach? Not necessarily at the moment itself, if that makes sense. And here's what the limit is written like. So you say lim, and then normally this part right here would be underneath the limit, but because I'm on a computer, I can't effectively do that without struggling a little bit. You'd say the limit as x approaches g of f of x is L. Here's a quick little aside that I think is interesting to talk about. There is a bit more to the definition of a limit, and it's called the epsilon delta definition. But as a quick disclaimer, and this is why it's an aside discussion, you won't need to know this for most calculus classes. In fact, you probably won't need to know this until you get into actual analysis. But it's still interesting to talk about. So you choose some small number, super small, like 0.000 repeating forever and ever 1. And it's greater than 0. So it's still positive, but it's super small. A number delta exists such that if the difference between x and the value is less than delta, but still positive, then the distance between the value and the limit itself will be less than that super small number. So basically this is saying that if the distance between x and g is super small, the distance between the value and the limit is also super small. So this kind of shows that the limit exists, if that makes sense. So if you didn't get anything from that, just remember limits describe what something approaches, even if the value itself doesn't exist. Let's look at some quick notation. Limits can be from different sides. If you're approaching from the left of a function, so the negative direction, you'd say the limit as x approaches 0 from the negative direction, or any value for that matter. You can say x approaches 4 or whatever. The same from the positive direction, you just say that with a plus. Let's take a look at this little practice problem right here. I want to talk specifically about 3 limits. I might think of more as I look at it a little longer, but let's first talk about x equals -2. So this piecewise function, x equals -2, is right here. And you can see that the function itself, goes up, and it looks like it would be at y equals 3.5 or so. But we see that because of this red dot, when x is equal to -2, the function is valued at 0, not 3.5, which is what you would expect. But if you're talking about limit, you would say that as you approach 2 from any direction, even if the value itself doesn't exist at 3.5, because the function approaches 3.5, you would say that the limit is 3.5, if that makes sense. So once again, even if the value doesn't exist, the value is at x equals 0 or y equals 0, you would still say that the limit of this function is 3.5. Next, let's talk about x equals 4. So x equals 4 is right here, and it looks really interesting. You see that from the negative direction, you have this constant at -2 coming in. You see that at y equals 0, you have the point is decided to be 0. And then from the positive direction, it looks like you have some sort of 1 over x. It's probably just 1 over x shifted over to the right. And you can see that it shoots up off to infinity. So let's talk about the limit here. So if you're saying just the limit as x approaches 4, you would say that the limit does not exist. And there's a couple reasons for that. First of all, because from the positive direction, you're shooting off to infinity. Because infinity is more of a concept than an actual value, you can't say that the limit approaches infinity. So you would instead say that the limit does not exist from the positive direction. And then if you're talking about the limit in general, you'd also be able to say that the limit does not exist because you're approaching x equals 4 at 2 different values. From the left direction, the limit looks like it's approaching -2. And as we discussed earlier, from the positive direction, your limit does not exist. So at x equals 4, the only limit you would be able to say that exists is the limit as x approaches 4 from the negative direction of f of x is -2. And then let's talk about x equals infinity. So as we discussed, a limit can't exist when it shoots up off to infinity like it does here. But as you approach infinity, what is happening is you see that it's approaching 0. So you would say that the limit as x approaches infinity is 0 because eventually when you get to infinity, x will be 0. So that's just some interesting things to think about. If you're shooting up off to infinity, the limit won't exist. But if you're approaching a value for infinity, the limit does exist. These are the most frequent times that limits don't exist. As we mentioned, f of x approaches different values from the left and from the right. This is what we saw at x equals 4 on this practice problem. You're approaching -2 and infinity from this direction, so it doesn't work. If f of x increases or decreases without bound, so if it shoots off to infinity like you see in 1 over x. And then the last interesting thing is when f of x oscillates between values, as I mentioned, this is really common with trigonometry. This is just sine of x. And you wouldn't be able to say that the limit of sine of x as you go off to infinity exists at all. You could of course say that the limit at a certain value exists because you can find that value. But if you say that the limit goes off to infinity, you wouldn't be able to determine which part of sine of x you're talking about, because as you go off to infinity, sine of x will always be one of these values between 1 and -1. So that's just something interesting to think about with limits. Once again, times that limits don't exist. These are the most common times that limits don't exist. Let's talk about indeterminate limits. So as I mentioned on the previous slide, limits can be found on graphs, data tables, and just simple algebra. And lots of the time when you're just using algebra, you will find an indeterminate limit. So what that means is, let's say that the limit is approaching 2. When you solve a limit, you just plug in what the limit is approaching to into the function. When you plug x equals 2 into this function, you will see that it doesn't work. F of 2 equals does not exist because you're dividing by 0. But as we saw on this first slide, the limit exists. We see that the function is leading to 4. So if you're doing a limit algebraically, you would have to be able to manipulate the equation for some way. So for example, with this problem right here, because the limit ends up being indeterminate, you use some algebra, you use difference of squares on the top. This is supposed to be difference of squares. Difference of squares on the top, and then you can cancel out the negatives. So x minus 2, you can cancel those out, and then you would see that indeed the limit is x equals 4 or y equals 4. And then let's talk about limits that involve infinity. So as I mentioned with this slide, limits often do involve some sort of infinity because it's a way for us to grasp the concept. This is a little more common when you get to improper integrals. That's a way later topic, so don't worry about that right now. But limits do involve infinity. I want to briefly mention something that I like. I actually really like this from calculus. It's just called end-behavior model. End-behavior model is really interesting because it's conceptual. You have to think about what the numbers will do at infinity because, like I've said, infinity is a concept. It's not an actual thing that you can work with. You just think of infinity. Let's take a look at this function. So f of x is equal to 1000x squared divided by x cubed minus 2x plus 1. And let's say that the limit of this function is approaching infinity. So even though 1000x squared is super big, and for the first couple of numbers, because 1000x squared is just so big, at the beginning, the top of the rational equation will be bigger than the bottom. But with end-behavior model, you're not thinking of the, easy to grasp numbers. Let's imagine that you plug 10 million as x. So x equals 10 million. What would this equation instead look like? When you get further and further and further out into infinity, you're going to start to see that the only number that really matters is this x cubed on the bottom of the equation. Because the bigger numbers you plug in, the bigger this bottom is going to grow. And the top won't really be able to compete with just how big x cubed will eventually become because of infinity. So with end-behavior model, you would say that this limit would probably approach 0 because you're dividing eventually by such a humongous number. So let's next talk about continuity. So continuity is a bit of a different idea, but it still involves limits. It's when a function is smooth. So you think about being able to draw something without picking up your pencil. For instance, a parabola. So y equals x squared. That's a continuous function because you can draw an entire parabola without picking up your pencil. And continuity is really important in calculus, so keep this in your mind. But as of right now, let's just talk about how continuity is guaranteed. So if the limit from the left, so that's right here. So if the limit from the left is equal to the limit from the right, so they approach the same value, and then if the value itself exists, then continuity is guaranteed. So to guarantee continuity, I like to call it the 3 keys of continuity. you have to have the value itself. So let's talk about this one again. So so this is a discontinuous function because you fail f of c. When you plug in 2 into this equation, you get undefined. But the limits from the left and from the right do match. So if f of c existed, like for this problem, then you would have a continuous function. But because it doesn't, continuity is not guaranteed. And this is sometimes that this is what discontinuous functions look like. I don't know what that word is. Discontinuous functions. This is what some of them look like. When talking about continuity, a great application is the intermediate value theorem. So intermediate value theorem isn't only a calculus concept, but it's really common in calculus. So it's a great way to talk about continuity and limits. It just states that if a function is continuous on a closed interval a to b, so we have that right here, a and b, it has to be closed. There's a value w where in between the y value of a and the y value of b is guaranteed to exist at some point c in the open interval a to b. So to kind of grasp this concept, let's look at this chicken. So why is the chicken crossing the road? It's crossing because of the intermediate value theorem, but it's also trying to get to the other side. If the chicken is trying to get to the other side, we can assume that its path is going to be continuous, right? We're not going to say that the chicken is going to disappear from existence and then just teleport to the other side of the road. The chicken is going to walk across that road or fly. So because the chicken's path is continuous, there's going to be a time, this is this green part, there has to be a time between the start of the road and the end of the road where the chicken itself is on the road. It has to happen. It's guaranteed to exist at some point. With the intermediate value theorem, we don't know when that point is. You know, the chicken could instantly cross the road and then spend a lot of time on the other side. Or the chicken could spend a lot of time on this first side of the road and, you know, do a couple loop-de-loops and then cross the road and end up on the other side. But because we know the chicken's path is continuous and that it must reach the other end of the road, we can assume that at some point, because of the intermediate value theorem, at some point the chicken has to be on the road. Okay, let's talk about this final concept, the one that I brought up at the beginning of the video. Can change occur in an instant? So let's first talk about slope. So slope is change. It's the rate of change between two different points. And slope is calculated with this. I'm sure you're very familiar. F of x2 minus f of x1 divided by x2 minus x1. So the difference in y and the difference of x are compared to each other, and then they are put in a ratio. So they're divided. I talk a little bit about, so this graph, because it's a linear line, the rate of change is average across the entire line. It never changes. But if you use this little equation right here with something like a parabola, the slope of the line won't be constant for the entire line. As you see in this picture, the slope is going to make a secant line. And if you remember, a secant line touches a curve at exactly 2 points. You remember from your geometry class. So because you make a secant line, is there a way to make a secant line instantaneous? If you think about a tangent line touches the curve at exactly one value. So if you can use rate of change, the slope, and make it a tangent line, that would describe the instantaneous rate of change. So here we go. Let's start proving that change can occur in an instant. Let's take two arbitrary points. Let's call this point the pink point and this point the blue point. The blue point is just going to be offset from the original point by some value h. So that's why h is there, is just to offset the points. So when you rename the points, your slope becomes f of x plus h minus f of x divided by x plus h minus x. So here we go. If we can use a limit and say that the limit of h approaches 0, the 2 points will move on top of each other, creating a tangent line. So here's a great GIF that shows that concept. When it replays, I'll talk about it. But yes, change can occur in an instant. Once again, what we did is we used slope, so the average rate of change, and it was represented by this secant line that's going to show up in a couple seconds. So right there, this is a secant line right now. But as you say that the distance between the 2 points is approaching 0, it becomes a tangent line. And once again, as we've been over, because tangency occurs at a single point, you're turning an average rate of change into instantaneous rate of change. So by using limits, you can make what is called a derivative. And this is going to be the topic of discussion for the next probably 3 or 4, maybe even 5 episodes of this series, because derivatives are super fundamental to what calculus is. And limits make it so that derivatives can exist. So I hope that you enjoyed this video. Once again, limits are pretty easy to conceptually understand. It's basically just what something approaches. And then, as we saw just now, limits are really important because you can make really cool things happen, like instantaneous change, by using just rate of change, just average rate of change. So overall, limits are super cool, and I hope that you guys are as excited as I am to explore calculus. Let's talk about the derivative in the next episode.